Webb just spotted a dusty, heavy galaxy 330 million years after the Big Bang. That means mature stars and metals showed up shockingly early. This rests on spectroscopy, not only pretty images. Immediate takeaway: galaxies grew faster than models expected. But how solid is it, and what could mimic it? Let's map the evidence cleanly, then test the wild claims. You stare into a deep field, faint smudges crowd the dark. Each smudge is stretched by expansion, like taffy pulled slow. Redshift is that stretch, measured from how colors slide redward. We care because Redshift timestamps the universe's baby photos. Light leaves blue, but space expands, so wavelengths grow longer. Longer wavelengths carry less energy and arrive looking redder. Astronomers write it as z, the fractional stretch factor. Rule of thumb: 1 plus z equals the stretch ratio. At z equals 13, wavelengths are 14 times longer. That light traveled about 13.4 billion years. The universe then was roughly 330 million years old, so a z13 galaxy is insanely early by any standard. We use filters to guess z, then spectra to confirm. Spectra show fingerprints from atoms, giving precise distances. They also reveal ages from shape changes across wavelengths. Example: in real terms, a sharp break means older stars. A flat blue slope means relentless, newborn star formation. Put simply, Redshift dates the scene, while shape hints maturity. So Redshift sets the clock and spectra sketch the story. Now we hit the instruments, because details live in photons. A spectrum is light spread into colors, then measured for dips. We care because dips mark elements and shapes reveal ages. NIRSpec splits near infrared light with prisms and gratings. It measures how much light drops across the bomber break. That break appears when older stars pile up at lower energies. See a steep drop and you infer a matured stellar population. Spot bright oxygen lines and you know stars already forged metals. The candidate shows a big break and strong continuum redward. That suggests stars a few 100 million years old already. It also shows faint emission, hinting ongoing star formation. Calibration matters, so teams compare multiple reductions carefully. They cross-check masks, noise models, and background subtraction choices. Tiny test: does the break survive when you shrink apertures? If yes, the feature is in the galaxy, not the sky. Reportedly, the break holds and the redshift sits near 13. Uncertainties remain, but the core signal looks repeatable. Net result: the spectrum screams early, enriched, and compact. Shift to the galaxy itself, a compact ember in the dark. By galaxy, we mean a bound system of stars and gas. We care because its mass and size test our formation models. Photometry plus spectra suggest a stellar mass near 1 billion suns. Its half-light radius seems under 400 parsecs, incredibly tight. That size concentrates gravity and helps fuel furious star formation. Star formation rate means how many suns form each year. In this case, estimates range between 20 and 50 suns yearly. Gas must flow in fast or merge from small neighbors. Cold streams from the cosmic web can feed that growth. Mergers also spike turbulence and pack gas toward the center. Dust reddens the light, making the galaxy look older, but the spectrum's break still argues for real maturity. Example numbers: mass around 10 to the power of 9 solar masses. Age indicators near 200 million years, give or take. Star formation turning gas into stars with fierce efficiency. So the picture is a tiny powerhouse, building unreal speed. Here is the skeptic's card: gravitational lensing can fake brightness. A lens is a foreground mass-bending light with gravity. We care because lensing can magnify, distort, and duplicate sources. Space curves around clusters, acting like a giant glass. Background galaxies stretch into arcs and sometimes form rings. Magnification boosts flux, so objects seem bigger and older. If magnified 10 times, mass estimates drop by the same factor. Redshift stays early, but the galaxy becomes less extreme. Mechanically, you map foreground halos, then solve lens equations. Models return a magnification, with uncertainties from unknown substructure. This field shows mild shear, but lacks obvious giant arcs. Weak lensing still matters, and stars in halos can microlens. Teams run multiple models to bracket likely magnifications. Example scenario: magnification of 3 reduces mass to manageable, but a magnification near 1 leaves the shock value intact. Bottom line: lensing could soften claims, but not erase them. Let's talk dust, the soot of exploded stars floating between suns. By metals, astronomers mean everything heavier than helium. We care because metals and dust require earlier generations of stars. Those first massive stars live fast, then seed the cosmos. Supernovae forge oxygen, silicon, and iron, then launch grains outward. Grains absorb blue light, and ray emit warm infrared glow. That glow can hide star formation, yet betray dust mass. Models for this galaxy imply significant dust for the epoch. We are talking perhaps 1 million solar masses of dust. That demands thousands of supernovae within a couple 100 million years. ALMA can test this with faint millimeter continuum measurements. A detection would clinch early enrichment and confirm high opacity. A non-detection would push models toward clearer, bluer stars. Example, a 2 sigma flux could still hide in current noise, so dust is the lever, tuning how old the light appears. Big picture, enrichment happened fast, or our assumptions must shift. Under the hood sits efficiency, the fraction of gas turned into stars. We care because small changes swing galaxy growth by orders. Halos bring in baryons, but feedback can kick gas back out. Stellar winds heat gas, while supernovae blow holes through clouds. Black hole jets can also choke inflows, even in dwarfs. To match this galaxy, average efficiency must run unusually high. Bursts could raise rates briefly, then settle after feedback fires. A top-heavy stellar mix would speed enrichment and boost light, yet that idea remains debated and needs cleaner tests. Dark matter sets the stage by shaping the halo potential. More massive halos cool faster and anchor deeper gas pools. Example math, build 1 billion suns in 300 million years. You need about 3 per year on average, not impossible, but spectroscopy hints bursts near 50, which need dense fuel. So either inflow was generous or feedback slept unusually long. What to remember, efficiency controls whether early giants can happen. So how do we decide signal or mirage? We care because the answer reshapes timelines for cosmic dawn. First, deeper spectra can lock the break in key lines. Longer integrations shrink noise and reveal faint nebular features. Confirming hydrogen bomber absorption would nail stellar ages. Measuring the ultraviolet slope constrains dust and hidden stars. Second, ALMA can chase warm dust with millimeter eyes. A clear detection sets dust mass and star formation obscuration. Third, lens models need sharper maps of foreground structure. Weak shear fields and subhalos tweak magnification by factors. New Hubble and Webb imaging can refine those constraints. Fourth, rest frame optical lines can confirm metallicity growth. Oxygen to hydrogen ratios show just how enriched it is. Example timeline, 1 observing cycle could settle half these questions. 2 cycles plus ALMA time could settle nearly all of them. Catalog cross-checks also matter for ruling out rare interlopers. Stitched together, these tests turn surprise into solid knowledge. Final word, targeted tests can separate drama from durable truth. So did Webb find something strange in the early universe? Yes, a compact, dusty galaxy appears far earlier than expected. The spectrum supports it, though lensing and dust remain caveats. Either way, the cosmos built structure faster than we predicted. If this breakdown helped, join me for the next deep dive. I post clear, chill explainers whenever new data lands. Tap subscribe if you want more space truths, minus the fluff. Thanks for watching and for keeping curiosity pointed skyward.